we get started on the new note sheet, are there any questions over either of the previous assignments, over either previous factoring assignments? Questions over the homework? So hopefully at this point, especially now that we've seen, especially factoring quadratics for the second, if not third time, going back through this, being able to do this is helpful, especially for ACT or college algebra going on, because being able to factor quickly does help us when solving certain problems. Now, what we're doing today, I call these special, quote unquote, special factors or special setups for factoring. These first few are perfect square trinomials. Essentially what that means is that they are going to be able to be written as a single set of parentheses squared. Now there was one on the first homework sheet, and if you write it as a single set of parentheses squared or have it factored out, doesn't make a difference. Both are the same. So if we look at this first one here, 4x squared minus 4x plus 1. First thing again, we want to look for greatest common factor. Is there a number or term in common with all three? And as we look at this here, 4x squared, 4x, and 1, there's not a variable in all three spots. And because one of the terms is 1, there's no greatest common factor other than 1. It kind of tells us there's not going to be one. So that means we'll move on to our two sets of parentheses with 3 spaces. Our third term's sign is plus. So that tells us that these signs are the same, and they're going to have to match the sign of the middle term, which is negative. So we have minus and minus. Now we're going to look at the factors of our first term, 4x squared. Now one of the nice things with multiplication product with factors, doesn't matter how we multiply 2 or more things, so I can look at the factors of x squared and the factors of 4 independently of each other. Factors of x squared have to be x and x. Factors of 4, we have 2 choices, 1 and 4 or 2 and 2. Which one do we want to try first? 2 and 2. And again, at this point, we're plugging them in to check and see if they're right. So we'll just pick 2 and 2, try it first. Now we need to find the factors of the third term. And the factors of 1 are 1 and 1. So the first one we're trying is 2x minus 1 times 2x minus 1. And we'll check this here. Now 2x times negative 1 would be negative 2x. Bless you. Negative 1 times 2x is also negative 2x. And negative 2x minus 2x, negative 2 minus 2 is negative 4, or negative 4x in this case, which is indeed the middle term, telling us that the factored form of 4x squared minus 4x plus 1 is 2x minus 1 times 2x minus 1. And this is the correct answer, and it is the correct way to write it. But because these two factors are the exact same expression, we can write it as 2x minus 1 squared. Because when we square it, all we're saying is that it's being multiplied by itself. Since the same two factors, or the factors are the exact same, we could rewrite it as 2x minus 1 squared. That is also the correct answer. We don't have to have both, but we can. And we've seen, especially with solving quadratics, if I can rewrite it as 2x minus 1 squared, the other side of the equation is just a number, we square root both sides, we can solve. That's one of the nice things with perfect square trinomials. But those two sets of parentheses have to be the exact same for us to rewrite it as a single set of parentheses squared. Questions on this here? 16b squared minus 40b plus 25. And again, I would always be looking for a greatest common factor. Because if there is, it's going to make it nicer, easier to solve. We have less factors to look at, less factors to work with, especially when factoring. And unfortunately, 16, 40, and 25 do not have any common factors between them. Because if we look at, say, 16, factors of 16, that could possibly work in all three. We have 1, 2, 4, 8, 16. 25 is not divisible by 16, 8, 4, 2, any of those there. So there is no greatest common factor among all three terms. Now we need to look at the signs. Since the third term is positive, our signs are the same and match the sign of the middle term. And our middle term is negative. So we have negative and negative. Now if we look at the factors of the first term from here, 16b squared, well, the factors of b squared are b and b. Now the factors of 16, we have a few. We have 1 and 16, 2 and 8, 3 is not a factor, but 4 and 4. Which one do we want to try first? 2 and 8. Now we need to look at the factors of the third term. Factors of 25, we have 1 and 25. 2, unfortunately, is not a factor because it's not an even number. 3, if we want to check 3, we would either plug it in or do 2 plus 5 is 7. 7 is not divisible by 3. Sum of its digits is not divisible by 3, so 25 is not divisible by 3. 4, we would just really need to divide it. 4 is not divisible, or 25 is not divisible by 4. 5 is, it's 5 and 5, and that's it. What do we want to try first? 1 and 25 or 5 and 5? 5 and 5. And we can check this here. 2b times negative 5, 2 times negative 5 would give us negative 10b. Negative 5 times 8b, negative 5 times 8 is going to be negative 40b. And negative 10b minus 40b, negative 10 minus 40 would give us negative 50. And that is not the middle term that we wanted. Now normally I would flip the constant terms on second terms, factor of the third term, but flipping the 5s won't actually change anything. So, and the reason switching the 5s won't change anything is still 5 and 5. Switching the 2 and 8 would give us the same thing. So we could switch to 1 and 25. So we can go 1 and 25. 2b times negative 25, 2 times negative 25 is going to give us negative 50b. Negative 1 times 8b would be negative 8b. And negative 50b minus 8b, negative 50 minus 8 would give us negative 58. So we can switch to 4 and 4. Because most likely switching to 1 and 25 is not going to change anything. Well, I take that back. It will change the values, but it's not going to give us the answer that we want. Because 2b times negative 1 would be negative 2b. Negative 25 times 8 is going to be negative 200b, giving us negative 202b, which is not the middle term that we wanted. Now, yes, we can switch from 2 and 8 to 4 and, or not 4, yeah, 4 and 4. And then switch over to 5 and 5. And if we check this here, 4b times negative 5, 4 times negative 5 would be negative 20b. Negative 5 times 4b would also be negative 20b, telling us that the middle term is negative 40b, which is the one that we wanted. Telling us that the factors for this here are 4b minus 5 and 4b minus 5. Or if we wanted to, just like the previous one, we can rewrite it as 4b minus 5 squared. So we can condense it. We don't have to, but we can if we want to. Questions on these here? Now, I say for the most part, these are special in that we can condense them, but our overall process and steps that we do for factoring don't change. Don't really change for this here. So we'll go on and look at the next one, next type of problem, which is this one here, n squared minus 25. Now this here is a special type. It is called our difference of perfect squares. If we have two terms being subtracted and they can be written as a number times themselves, they are perfect squares, they will factor in the form of a plus b times a minus b. Now for some of these here, the way that we went about it is first looking to see if the two terms are perfect squares. If they are, we can use this here. One of the things to also, again, look for is greatest common factor. Even though we do have two terms being subtracted, they can still have a greatest common factor that can be factored out. And if we look at this here, n squared minus 25, there is no greatest common factor, nothing in common with both terms. And we...
Because the 25 doesn't have a variable on the side of it, so would that not be like a...
That would be C, our third term, yes. Because really, our middle term in this case is 0. So n squared minus 25 is considered the same as n squared plus 0n minus 25. Yeah, so our 25 would be considered our C. If we're talking about quadratics, a squared plus b, or our ax squared plus bx plus c. It is our constant term, our C term. And it would be considered the third term for factoring. Yes. Now, if we want to look at it in terms of a squared minus b squared, a is the number that times itself is our first term squared. So what times itself is n squared? Well, that'd just be n, because n times n is n squared, yes? What times itself is 25? 5. Now, what we're doing here is just getting it in the form of a squared minus b squared. So now we know that the a term, the number or variable representing a is n. The number representing b is 5. So it's going to be a plus b times a minus b is how it's going to factor. So a was n, so we have n plus b, so n plus 5 and n minus 1. And that's it. And normally, especially with perfect squares, we just say we're done. If I wanted to check, I can. There's nothing wrong with that. N times negative 5 would be negative 5n. Positive 5 times n is going to be plus 5n. And negative 5n plus 5n is 0n or 0, because there is no middle term, so that is the correct middle term. So n plus 5 times n minus 5. And that's it. Questions on this here? These are some of the nicer ones, I think, especially once we see what the two values are. Plus, minus, we're done. Be ready for the next one. 16n squared minus 9. So, it's still of the form a squared minus b squared is equal to a plus b times a minus b. So we can rewrite it in the form of a squared minus b squared, so we see what a and b are. What times itself is 16n squared? 4. And then we would have our n, because 4 times 4 is 16, n times n is n squared. So 4n times 4n is 16n squared. What times itself is 9? 3. So a plus b would be 4n plus 3. And a minus b would be 4n minus 3. And that's it. And if you're not sure if one of the two numbers is a perfect square, you just take the square root, because the square root is finding what number times itself gives us the number inside the square root. So the calculator can tell us that the square root of 16 is 4. (4m squared minus 25). I didn't talk about it last one. We would look for greatest common factor. There's not one. And we do have two terms being subtracted. So as long as 2m squared is a perfect square and 25 is a perfect square, we can do this. Well, what times itself is 4m squared? 2m. What times itself is 25? 5. So this is going to factor into the form of a plus b times a minus b, where a is 2m and b is 5, so we get 2m plus 5. And then our a minus b would be 2m minus 5. I will say, we don't have to put the plus first. Because of our properties of multiplication, 2m minus 5 times 2m plus 5 is the exact same answer. There is no difference between the two. We just got to put one or the other. Now do be careful to make sure that we don't flip the terms. If the variable is second, we're going to leave it second. The first term, the term before the minus, is going to go first. The term after the minus has to go second. Now this one here looks a little different, yes? Because we have a to the fourth minus 9. Now there's not a greatest common factor between the two terms. But let's see here if both of these are perfect squares. Now 9, we'll start with it first. What times itself is 9? 3. Is it possible to write a to the fourth as something times itself? A squared, because a squared times a squared would be a to the fourth, because a power of a power multiplies. So our 2 times 2 would give us 4, yes? So we're still able to write it in the form of a squared minus b squared, yes? Which means this would still factor to a plus b times a minus b. But for us, our a term is now a squared. Excuse me, our b term is 3, so we get a squared plus 3. And we would also get a squared minus 3. Questions on how we got to this point here? Now we can say we're done as long as neither one of these factor. Because the degree is bigger than 1, there's a chance that they get factored. A squared plus 3, a squared is a perfect square. As we've seen it already, we've seen it up to this point, it's a times a, yes? But we don't have a sum of two squares. there is no factoring that works for that there. But the other set of parentheses, we do have a difference. We have two things being subtracted. A squared is a perfect square, yes? A times A. Is 3 a perfect square? No. So, this does not factor any further. That is the final answer. A squared plus 3 times A squared minus 3. That is as simplified as it gets. It is possible to factor A squared plus 3 and A squared minus 3, but A squared plus 3 would have complex factors. We don't consider that as a part of factoring, that you have to find the answer and then get it back in factored form. A squared minus 3 does factor, but its factors are irrational, because actually the first one's complex, irrationally complex, and this is just irrational, but we don't look at irrational or complex factors. So this is as far as it goes. This seemed, especially before we did this, seems like it should be very different than our completing the square, or our difference of perfect squares that we've been doing, but did it really change that much? No, as long as it follows the pattern, it works. So if we look at k to the fourth minus 36, as we just said with x to the fourth, I could rewrite k to the fourth as k squared squared. If 36 is a perfect square, it would be, we're good? 6. Because we can take the square root of 36, and it is 6. So that tells us that this is k squared plus 6 times k squared minus 6. K squared is a perfect square. Our k squared plus 6 is a sum of two squares. Well, we don't have a sum of two squares at all. So that's as far as that goes. Can't factor k squared plus 6. K squared minus 6 would work if both k squared and 6 are perfect squares. K squared is, but 6 is not. So that's as far as it goes. Questions on this here? So really when we're looking at quadratics, or we're looking at expressions when that degree is bigger than 1, we have to just double check and make sure that it doesn't factor further. X to the fourth minus 81. We're going to look at one more of these here of this type. X to the fourth, we can say is a perfect square. And to write it in our a squared minus b squared form, we would say that it's x squared squared. What times itself is 81? 9. So that tells me this will factor to x squared plus 9 times x squared minus 9, yes? Now, any questions on this here before we move on? So we feel good about getting to this point, yes?
What if you come across a question that they can't factor, or like you can't, it's a number that can't times itself?
Then we're done. Because like on the last one, k squared minus 6, k squared and 6, it's not perfect squares, it doesn't factor, so that's as far as it goes. If it starts out that way, if it starts out not factorable, like we don't have perfect squares, first thing I'd look for is greatest common factor. Is there a common factor between both terms? If there is, we factor it out and check again. Like on the homework, the first one where we factored out 5, and that's all we could do, because the result from it, what we had left over with the quadratic, wasn't factorable. We can't say not factorable, because greatest common factor is considered factoring. That worked. But if we looked at this and we'll just say it was 82, no perfect squares, no common factors, that's as simplified as it gets. We can't do any factoring to it. And if we were solving at that point, we'd have to default to other methods to solve it from there. Does that answer your question? Awesome. Now we'll just check this here before we move on. X squared plus 9, we don't have a sum of two squares. Just doesn't work. X squared minus 9 would work as long as we have two perfect squares. X squared is a perfect square, it's x times x. Is 9 a perfect square? Is there a number multiplied by itself that gives us 9? 3. So what that means is we're going to bring this down. Because we can say x squared plus 9. Well, for this part here, we do have our term being multiplied by itself is x. X times x is x squared. And our 9 is 3 squared. And what that tells us is that this is going to factor to what? X plus 3 times x minus 3. Because x squared and 9 were both perfect squares, our x squared minus 9 did factor one more time. It is a perfect square, a difference of perfect squares. So we had to simplify it one more time. Questions on this here? So really what we did is what we did on the first step. We just applied it to x squared minus 9 and did it one more time. So x squared plus 9 times x plus 3 times x minus 3 is the final answer. Questions? Yes? Mm-hmm. Yeah, because this would be considered factored. However, this last one is factored completely. And that's the big difference. In most, the ACT, in most places we'll see, they will ask you to factor the following expression completely. So x squared plus 9 times x squared minus 9 is factored, but it's not factored completely. If there's a greatest common factor, if there's any way to reduce it, and it has to be factored completely, we've got to reduce it. If there's a common factor, it has to be factored out. If it's not, it is not considered factored completely. Which seems minute, but tests, ACT will do that. They will throw x squared plus 9 times x squared minus 9 as an answer choice when factored completely, which is wrong because it needs it all the way down. All right, questions on any of this so far? Because this is kind of new, not really, it's just taking a step beyond what we've done. Biggest thing I will say, especially when you take college algebra, this is the big difference from what we'll do in here to what they do there. It's just taking stuff that we have learned a step further, expanding it out. Now, one of the new factoring methods we will learn is this one here. Sum of two cubes and difference of two cubes. Sum and difference of two cubes, we do have both sum and difference. And this works if the two terms are perfect cubes. They are perfect cubes. They are a term or number that can be multiplied by itself 3 times. Now, one of the nice things is you do not have to memorize your cubics because, well, the calculator can 3 second root. We can take the cubed root. It will tell us what the cubed root of a number is. Can't do variables, but it can do numbers. Yes. Graphing calculators will do it also. A few more buttons to press to get to it, but it can do it. Because if we're looking at the graphing calculator, we can do math. Go down to number 4, and it will do that there. Sum of two cubes and difference of two cubes. Now the general form for sum of two cubes and difference of two cubes, if you're going to, I would write it next to it, you can, is going to be these two formulas here. The top one is the sum of two cubes. The bottom is the difference of two cubes. Now, there is some things that are very nice with this here. In both forms, in the first set of parentheses, our a and b terms are both to the first power. For sum, it's a plus b. Difference, it's a minus b. We just have a and b to the first power. We see that there, yes? Let's look at the bigger set of parentheses. If I look at my a term, it's to the second power, to the first power, and then there's not one listed. And the reason for that is, well, you don't have to write it in. I wouldn't necessarily write it in. It's really to the 0 power, because we're going 2, 1, 0. And anything to the 0 power is 1. So we're really saying a to the 0 times b is just 1 times b squared, which is just b squared, yes? Now let's look at our b terms. Well, I'm going to go the opposite direction, because at the end we have b squared. In the middle we have b to the first, which means next to a squared, realistically, we have b to the 0. So our second term, our b term, is going 0 to the 0 power to the first power squared. So the exponents with our second term is going up. Our exponents with our first term, our a term, is going down. We kind of see that pattern. Because really that's all that's, we haven't done a whole lot, but that's just looking at what it does. And the reason I'm pointing this out is because, well, that's for the sum of two cubes, yes? Let's look at difference of two cubes. As I said already in the first parentheses, it's just that first term, second term, AB. Whatever times itself is going to go in those two spots. In the bigger set of parentheses, we have a to the second, a to the first, and no a term. Really, it's just to the 0. Our b, we're missing b in the first spot because it's to the 0 power. Then we have b to the first and b squared. Wait a minute, those powers are the exact same for difference in squares, yes? So what's only the real difference between these two is the signs. For signs, for the sum of two cubes, when we're adding two cubes, it's plus, minus, plus. When it's difference, it's minus, plus, plus. So really, the only difference is the signs, and it's keeping those straight. All right? And that the signs are going to be the same, opposite, always end on a positive note. So for sum, we have plus, minus, plus. Yes. Yes. And for difference, we have minus, plus, plus. Same, opposite, always end on a positive note. So if we look at the first example of this here, x cubed plus 125. We want to see first if it is a difference of perfect squares. So we need to see, is x cubed, can it be written as a number or term multiplied by itself 3 times? Well, yes, it would be x. So that's telling us our first term, a, in this case, is going to be x. Now we need to see if 125 is a perfect cube, if we can write it as a number times itself 3 times. One way we can check is we can grab the calculator, say 3, and get our x root, and type 125 in. And 125 is 5. Because 5 times 5 is 25. And 25 times 5 is indeed 125. So we have 5. Now the two ways we can do this from here, one is I just take the sum of two cubes formula that we have written and just replace a and b with those terms. And if I wanted to do that there, I just look at the form of a plus b times a squared minus ab plus b squared, and we just replace a and b. This is just the formula, because I'm just writing it straight from the notes, copying it down. Because a, in our case, is what? Our first term is x. So if we look at this here, every place where there's an a, I'm going to replace it with x. So in the first set of parentheses, that a plus b, a is going to become x. Our a squared is going to become x squared. The a and a times b is going to be x. And that's the only other place it shows up. Yes, sir?
So, you know, in the parentheses,
Mm-hmm.
you have other parentheses, the x, if you need to add those.
So really all I did with the parentheses was just putting spaces for all the terms. So a here give us those three parentheses. Now, we also have b, that's going to show up here, here, and here. Now, our b term in this case is 5. So in each place b shows up, we would replace it with 5. Okay? Now, the last thing we need to do is simplify where needed. And all that means is if we look at each spot, because in the first set of parentheses, we just have x plus 5. There's really nothing needing to be simplified there. X squared, we are going to square that spot. Now, here there's just x, but if there had been 2x, we square both the 2 and the x, giving us 4x squared. In the middle spot, we have x times 5, which would be 5x, plus 5 squared. 5 times 5 gives us 25, telling us that we have x plus 5 times x squared minus 5x plus 25. Questions on how we got to this here? Now, as we said earlier, let's focus in, that when we have that x squared, that degree is greater than 1, there's a chance that it does factor. However, with some indifference of perfect cubes, the quadratic part of this, in this case x squared minus 5x plus 25, will never factor. This part of the expression will never factor. It does not factor. But this here would be the factored form of x squared plus 125. We will pick this up tomorrow.